As summer ended and temperatures dropped, some of our honey buckets had turned solid. We used to sit them on the plate warmer or near the radiator, but most of this heat was lost into the room. So I decided to build my own warming cabinet. Commercially available honey warming cabinets cost upwards of £1,500 and use a kilowatt of energy. Instead, many beekeepers make wooden boxes and insulate them and put bulbs or tube heaters at the bottom. They work, but they still waste energy and there can be fire risks with them. Then I realised fridges are super insulated and already built to manage temperature differences between the outside and the inside, albeit cold inside normally. I found this old Williams commercial fridge on Gumtree. Williams are an Australian brand known for coping not only with kitchen heat but also with the hot Australian weather. It no longer cooled, so the pizza shop was scrapping it. It was perfect and I rescued it. Before starting, I checked the insulation, the U value. Lower numbers are better. This is basically the amount of energy lost through a metre square for every degree difference between inside and out. For example, double glazing is about 2 watts per metre squared. The eco homes I built 2 years ago are about 0.3. This fridge sits at 0.6 watts per metre squared Kelvin, perfect for trapping heat efficiently.
Once home, I got to work. I'm not exactly handy, I don't really do DIY, but I loved getting stuck into this project. I removed the PCB control panel from the top, which left a gaping hole in the lid where the old controls used to sit. Then I moved on to the compressor and pump. Since it was an old fridge that no longer cooled, there was hardly any freon left inside. I stripped out the compressor, the copper pipes and the cooling grills, basically everything related to refrigeration, leaving nothing but a clean, highly insulated box ready for its second life. After that, I removed all the original cabling and completely rewired the unit, running a mains feed in from the rear to where my new control panel would be mounted. From there, I wired 2 circuits down to the base where the heating system would sit, and 1 into the top to repower the fan. The fan at the top, which originally blew cold air into the fridge, was faulty, but I plan to reuse it for cooling in the summer. If the honey gets too warm, enzymes can be damaged, so I wanted a safety system that would pull in cool air automatically. I'd run a pipe down to the bottom, which acted as the air intake. I found the exact replacement model on a spare parts site for £90, but then discovered a compatible version on Amazon for £19, and it arrived the very next day.
I started with tube heaters mounted on the stainless steel base, all wired into a smart controller that could handle both heating and cooling. I even reused a strip of wood panelling to mount the control panel neatly on top. But the tube heaters weren't ideal. They have internal thermostats that keep cutting out once they reach temperature, so they never stay hot long enough to properly warm the cabinet. To try and even out the heat, I added 3 120mm fans at the bottom, angled to blow air diagonally across the heaters. Unfortunately, this didn't prevent the tube heaters from shutting off, but it made a huge difference to circulation. The temperatures across the whole cabinet now are beautifully even. After doing a little more research, I replaced the tube heaters with ceramic bulb heaters, the kind that reptile owners use. They give out steady, radiant heat without any light and without cycling off. I kept the heaters at the bottom where the most efficient heat rises, and I set up 2 circuits, a thermostat-controlled steady circuit for normal running, and a timed 2-hour boost circuit, driving a 3rd heater to power through a cold start when the honey is still solid. Once it's warm, the boost drops out and the thermostat takes over, maintaining the perfect temperature. I also replaced the top fan. I reused it as a summer cooling system so that if the cabinet ever gets too warm, the fan kicks in and pulls in air through a pipe ran down the back, which acts as the air intake. Heaters at the bottom, cooling at the top. Simple physics, and it works perfectly. So the cabinet now reaches 43 degrees Celsius in just 11 minutes, and it holds steady between 42.7 and 43.5 degrees, using a fraction of the energy other cabinets use. Perfect for liquefying honey. It fits 8 14-kilo buckets and 150 jars in, all at the same time. It costs about 2 pence per hour to run, compared to 25 pence an hour for the commercial ones. Before building it, I calculated the energy needed to liquefy a 14-kilo bucket of honey. Turns out it's about 2 megajoules, or about 0.56 kilowatt hours. Testing confirmed when the cabinet was full, each bucket used about 0.6 kilowatt hours. That's 2.2 megajoules, almost spot on. The interesting thing is how the cabinet behaves once it's up to temperature. At first, it takes a bit of energy to liquefy. It's thick and heavy, so the heaters run almost constantly during that initial phase. But once it's liquid and warm, the controller barely has to switch the heaters on. The honey itself holds and radiates heat, and the excellent low U value of the fridge prevents most of that warmth from escaping. High energy use only when needed, then minimal running cost. It's efficiency by design. So, from an old fridge destined for landfill to an efficient honey warmer that costs pennies to run, not bad for a weekend project. If you're into sustainable beekeeping, give it a go. It's simple, safe, and sweetly satisfying.